Today's lesson is about how two planes may intersect. And this is really just to help prepare you for the final lesson, which is about how three planes can intersect, which is quite a bit more complicated, but uses a lot of the same ideas as what we do today. So again, I'll try to keep today as clear and straightforward as possible, but tomorrow is really the the one I would focus on. Now, there are three different ways that two planes can exist in space. Okay, number one, they could be parallel and on top of one another, so to speak. If you think about this as like two floors, like the second floor of St. Marcellinus and the first floor, they are parallel to one another and they never meet, right? The first floor and the second floor would never intersect, right? I mean, you need to take the stairs or the elevator or something to get from one to the other, but you can't just keep walking on the second floor and then get to the first floor, right? At least, I suppose you could fall off the side of it, but you get my point. Okay, in this case, the normals, right? Remember, how do you tell if planes are parallel or not? You compare their normals. So if what you get here is you get the normals are parallel, okay, but you will find that when you try to test a point from the first plane in the second plane, it doesn't work. On the other hand, if you try this when the two planes are in fact on top of each other, so you think of this as one plane as your desk and one plane as a piece of paper on your desk, that everywhere on that paper is also on the desk, right? On that plane. They're in common. So every point on the plane is a solution. So again, what you would notice in how to tell these two apart, you would notice that both of them are parallel, and then you would try to test a point. If the point works, you're in case 2, and therefore every point must work. If the point doesn't work, you're in case 1, and no other point would work. Okay, and so that's quite straightforward. So always when you're looking at a case of two planes, the first question you should ask is, are they parallel? Because if you know that they're parallel, that immediately cuts it down to either this one or this one, and then you just test a point and you're done. On the other hand, if you show that they are not parallel, it must be the case that they intersect, and it must be the case that they intersect in a line. Right? A line must be how those things intersect. Again, think of the classroom, and think of the plane that represents the floor. So that we said was the XY plane, right? Because there's no vertical movement on the floor. Then consider the board, which is the YZ plane. You can move up and down, you can move left and right, but you cannot move forward and backwards, otherwise you'd be off the plane. Where do those two things meet? Where does the floor meet the board? They meet, along a corner, right, which is a line, right, at the front of the room. And it's not just one point, it's many points, right? It's that entire line where those two sort of surfaces connect. Okay? Every time you do not have parallel planes, you must have intersection in a line. And this is, if you think of these three, the analogy would be to lines in 2 dimensions. Lines in 2 dimensions can be parallel distinct, parallel coincident, or they can intersect 1 dimension lower than they exist. They exist as a 2D object, but they can intersect at a 1D object, which is a point. Planes, right, are a 3D object that can intersect by a 2D object, right, which would be the line. And so 3 planes is a lot like 3 planes in 3 space is a lot like let me try this one more time. 2 planes in 3 space is a lot like 2 lines in 2 space. Parallel distinct, parallel coincident, or they meet in one place, and that place is either a point if you're talking about lines, or a line if you're talking about planes. So it says determine the line through which these pair of planes intersect. Okay, so how do we actually achieve the location of this line? Okay, so first of all, let's note that normal 1 is not equal. Oh my goodness. Okay, normal 1. I think it's this, isn't it? No. Equals slash? No. Slash equal. There we go. Okay. Normal k times n2 vec. Okay? Because just look at them. I mean, it's 2. You have 2, negative 1, 1. And there's no way you could get 1, 1, 1 out of that, because in order to keep the z the same, the k would have to be 1, and obviously that doesn't work for the other ones. So they're non-parallel. So immediately here they are case 3, and they intersect in a line. Now, how do you actually find where they intersect? Now, this is a little bit challenging. So, make sure you follow closely with what I'm going to do. So, what you do here is the method here is to eliminate a variable first. So let's just say step 1 is eliminate a variable. So step 1. Okay, so here we go. So what I'm going to do is I'm going to write the two equations on top of one another. 2x minus y plus z minus 1 equals 0. X plus y plus z minus 6 equals 0. Now you can see I could eliminate z by subtracting, eliminate y by adding, or eliminate x by doubling the second one and then subtracting. Now, of course, which of those is the easiest to do is obvious to me. Would be we're just going to add them and we'll eliminate y. Okay? So when you add them together, you get 3x plus 2z minus 7 equals 0. Okay? Now, at this point, what we need to do, so all of our solutions, right, will fit this pattern. And so what you do now is you create, so number 2, introduce a parameter t, because we know that a line in 3D is going to need a parameter eventually, right? Introduce a parameter t and replace either remaining variable with it. So for instance, let's say let's do it this way. So let's say is there an easier one? I think it's probably easier to use z, but it doesn't matter. You can use either one. Okay, so you say let z equal t. Then you isolate x. So 3. 3. Isolate the other variable in terms of t. Okay, so 3x plus 2t minus 7 equals 0. So we're going to go 3x equals 7 minus 2t, and therefore x equals 7/3 minus 2/3 t. Okay, so we have that. Now what we're going to do is isolate the original variable, the one you eliminated, and get it in terms of t. Okay, so let's go back to, it doesn't matter, you can use either equation. Let's use the second one. So x plus y plus z minus 6 equals 0. Okay, so x plus y plus z minus 6 equals 0. So x, I know, is 7/3 minus 2/3 t. Y is y, we don't know. And z is t, minus 6 equals 0, right? So we just have to isolate y. So get y equals 6, take away t, plus 2/3 t, and then minus 7/3. Okay, so we get y is equal to, let's see, 6 would be 18/3 minus 7/3. And then we have negative t and positive 2/3 t is negative 1/3 t. So you'd get this idea that y is equal to 11/3 minus 1/3 t. Now, what you now have, right, z equals t and x equals, what was x again? 7/3 minus 2/3 t. What I just created, right, is the parametric equation of a line. And I know, right, so the solution is the line represented by this parametric, or these because it's multiple, these parametric equations. Okay, so let's write it in vector forms, and then we can draw it. So r is equal to the point, right? So let's think of the point. 7/3 is the x, 11/3 is the y, 0 is the z, plus t, and then let's look at the direction vector. Negative 2/3, negative 1/3 for y, and then 1 for z. And again, t is in the real numbers. Okay, let's investigate this, and I'll just show you how this would work visually. Okay, so let's draw the two planes first. So we'll go to 3D graphics. Okay, we'll draw the first plane is 2x minus y plus z minus 1 equals 0. So there's the first plane. Second plane is x plus y plus z minus 6 equals 0. Okay, so there's the second plane. Now let's remove the that one, so we're just focusing on these two. Okay, now what you can see, obviously, is that they intersect in a straight line. They intersect in this straight line right here, right, where the two sheets sort of cross one another. And if you look at them as from the side so that they become sort of 2D, can't quite get this perfect, but you can kind of like narrow down they intersect along this line into the page, right? Now I believe GeoGebra can just do this. We can just intersect EQ1, EQ2, and it does it for you, but it can be tricky when it does it for you to interpret this, like what are these decimals that it created. But it can do it, right? So it can find you where they intersect. They intersect in that straight line. Now what did we say? What did we say they intersect at? We said they intersect at, the line we had was 7/3, 11/3, and 0. So 7/3, 11/3, and 0 was the point, right? And you see that point is indeed on there. It's on the intersection. And then the direction vector we said was negative 2/3, negative 1/3, and 1, which, you know what, we might as well just make that a little easier. So r vec equals 7/3, 11. So you can't change the point, right? But you can change the direction vector. We'll just multiply it all by 3. So we'll go negative 2, negative 1, 3. Right? So that would be our direction vector. So m1 equals negative 2, negative 1, 3. Okay, now what I'm going to do is I'm going to draw a line that passes through point A with direction vector m1, and my line is the perfect line of intersection of those two planes. Okay, so again, GeoGebra is really handy. It helps you. It certainly helps you get the direction vector. It doesn't always help you get the point. Like which point this is can be a little tricky. But anyway, you could definitely use it to check your work, right? And then you can use it to get the answer too. You just have to be a bit careful with interpreting what the point means. You can also just change your rounding to 5 decimals and try to get it more accurately. But anyway, it doesn't matter. They're both right? Both of them are the equation of the same line. They just picked a different point to start at, but it's a line with a point and a direction vector is still the same thing, right? It's just their point is somewhere else. Let's draw their point. 2857, 3.929, negative 0.786. So, they just picked point B. They just picked this point down here instead of the point I picked, right? So it's a bit different. Same answer though. So how do you do this, right? Let's just review what it was I did. I eliminated one of the variables. So whichever one you want, it doesn't matter. I eliminated y because I thought adding them together would be pretty easy, but you could subtract to eliminate z. There's different ways you could do it. Once you have eliminated one, you replace another one with a parameter, okay, and you start to isolate the other ones in terms of that parameter. So you get x isolated in terms of t, and then you get y isolated in terms of t. And once you have that, what you actually have is the parametric equations of a line, and you know that the solution you're looking for is a line. So you just say these parametric equations are the line that would represent this intersection. Let's try another one. So here we have 2x minus y plus 3z equals negative 2, and then we have x plus 0y minus 3z equals 1. Okay, now you still need to isolate Actually, oh, we've got some time. Let's find out if you don't need to isolate. So let's say, let's have a theory here. Since there is no y in equation 2, let's just start with step 2, since y is already kind of eliminated, right? So we have x minus 3z equals 1. So you say let, I always mix up which one will be easier. So let z equal t. Then x minus, I guess it's easier to make x equal t. No, I always do this wrong. Okay, let z equal t. So x minus 3t equals 1. So x equals 3t plus 1. And then we go into equation 1, and we find y in terms of t from equation 1. And we get 2x minus y plus 3z equals negative 2. So x I'm going to replace with 3t plus 1. Y is still y. Z I'm going to replace with t. And I get negative 2 on the other side. So 6t plus 2, take away y, plus 3t equals negative 2. And I get y. So let's bring y to the other side. So 9t plus 4 equals y, right? Because the negative 2 comes over, makes positive 4. The y goes over to that side. So my hypothesis is that the answer is, so again, the line that we want would be, okay, the x coordinates are 1, the y coordinates are 4, the z coordinates are 0, plus t. Now what are the direction vectors? The x has a 3 on it, the y has a 9 on it, the z has a 1 on it, where t is in the real numbers. Okay, so let's see if that's right. I am not sure this will work, but I think it probably should. Okay, so let's draw the first plane. 2x minus y plus 3z equals negative 2, and x minus 3z equals 1. Okay, so there you go, something like that. Okay, now my hypothesis is that 140 should be on there. So far so good, right? I found a point that's actually on there. And then the direction vector of the solution is 391. I'm thinking that looks pretty good. So we go line A with point A and direction vector M1. And there's the solution to that one. Okay, that line is exactly where those two planes cross one another. And what we could do intersect EQ1 and EQ2. So get GeoGebra to give us the answer. You can see GeoGebra gives the same direction vector, but it picked a different point. But then what we can do is we can go distance between F and G, and it comes up with 0. Our two lines have no distance because they are the same line, right? So GeoGebra's solution and my solution are the same. It's hard to see that sometimes because GeoGebra often picks, I can't figure out how it's picking this point, I don't know. But the two lines are still equal, right? The two lines are the same. So there you go. If one variable starts eliminated, you can just skip the step where you're eliminating a variable because you don't need to. Okay, which pair of planes are parallel and distinct, and which are parallel and coincident? So first of all, of course, you notice for the first one here, mercy. Let's do it as a table. What is with the margin on this document? Sorry, I shouldn't complain about this audibly. Okay, direction vector number 1. So normal 1 vector is 3, 2, negative 5. Direction vector of the normal number 2 is 6, 4, negative 10. And you can easily see that they are parallel. Since 2n1 equals n2. Now the question is, are they in fact the same or not? Now there's an easy way to do this. So there's a couple of, there's all of the ways are easy, but which way you want to do is up to you. You can, number one, pick a point from the first plane and check in the second. Number two, you can attempt to eliminate a variable and interpret the result. So let's do solution number one. So a point that's on the first one would have to be 0, 1, 0, right? Sorry, 0, 1, 0 must be on the first plane, because if x is 0, you get 3 times 0, 2 times 1 is 2, 5 times 0 is 0, and then you have 2 take away 2 is 0. So that point is definitely on there. Check it on the second plane. 6 times 0, 4 times 1 is 4, 10 times 0 is 0, subtract 4 is 0. So you go 0, 1, 0 is also on second plane, so they are coincident. Okay, so they're coincident. Now, let's say we wanted to do solution number two, where you try to eliminate a variable, right? So we're going to go 3x plus 2y minus 5z minus 2 equals 0. Underneath it, 6x plus 4y minus 10z minus 4 equals 0. Let's take the first line and double it, 2 times L1, and we're to L1, we get 6x plus 4y minus 10z minus 4 equals 0, over top 6x plus 4y minus 10z minus 4 equals 0, and then you get 0 equals 0, which is true for all values of x, y, and z. So since we did the elimination and we found a true statement at the end, we found that no matter what x, y, and z you choose, the statement would be true. Therefore, they intersect everywhere. Okay, infinite solutions and coincident. Let's try the same thing on the second one. So again, you can see they're parallel because you have 2, negative 4, 3, and then you have 4, negative 8, 6, and one of them is just doubled from the other one. So now what we're going to do is we'll do method 1. So let's test a point. So on that first equation, I can see the point 2.5, 0, 0 is on equation 1. Now if I try, let's sub in 2.500 to equation 2. So you get 4 times 2.5 minus 8 times 0 plus 6 times 0 minus 14. And I get 10 minus 14 equals 0, which is negative 4 equals 0, which is always false. Therefore, they never meet. Okay, so you just show that the point that's on one is not on the other. Since they're parallel and they do not share that point, they cannot share any points. Let's try doing it in a method 2. Okay, method 2 would say we try to eliminate a variable. So 2x minus 4y plus 3z minus 10 equals 0. Underneath it, we have 4x minus 8y plus 6z minus 14 equals 0. Again, I'm going to do 2 times equation or plane 1, so pi 1. So usually a plane is indicated by pi, so I should change this from L to pi, right? Because this is not a line. It's not a line. It's a plane, and usually we use L for line, so that shouldn't do that. So let's double the equation for pi 1. You get 4x minus 8y plus 6z minus 20 equals 0. Underneath it, 4x minus 8y plus 6z minus 14 equals 0. You subtract the two. Negative 20 subtract negative 14 is negative 6, and this is never true. Therefore, there is no intersection, so they are parallel and distinct. Okay, so that's good. So it's pretty easy to check. You check a point or do your regular elimination, and you'll find a statement that makes no sense. The reason I think doing it in method 2 is good is because it's the same thing you're doing when they do intersect, and of course you're not going to know in advance which one of these things they are, and it's kind of helpful for tomorrow, for the next lesson. So anyway. Okay, last question. determine an equation of a line that passes through the point 5, negative 2, 3, and is parallel to the line of intersection between these two planes. Okay, so what we would want to do here, so the line we want to create needs a point and a direction vector. The point is 5, negative 2, 3. That was given. The direction vector will be the same as the direction vector which intersects, the direction vector of the line, which, the line of intersection, let's say, between pi 1 and pi 2. Okay, so we're going to need to solve the intersection, take its direction vector, and then just pop it on to this point instead of whatever point we get. So let's find the intersection of the two planes. Okay, so x plus 2y minus z equals 6. 0x plus y plus 2z equals 1. Again, since x is already eliminated, skip step 1 and go to step 2 with pi 2. So take the second one and go there. So the second step says y plus 2z equals 1. Now, my little rule here for you should always let t be the variable attached to the most irritating coefficient. It looks like you should let y be t here because it's all on its own, but make z t. Let z equal t. Pick whatever one has a coefficient and make it t. If you go back up to the very first question I did, I let z be t. I should have let x be t, because when I picked z, I had to divide everything by 3. If I had picked x, I would have had to divide everything by 2, and I would have worked with 0.5, so it would have been easier for me. Okay, so it looks like you should it doesn't matter, of course. Both of them are right. I say always let like it's some rule. It's not a rule. It just makes it a bit easier. If you let the variable attached to the most irritating coefficient bt, then you'll find you don't need to divide by an irritating number. So let z equal t. Then y plus 2t equals 1, and y equals 1 minus 2t. Okay? Then what I can do is I take equation 1, and I say x plus 2y minus z equals 6. X plus 2 bracket 1 minus 2t minus t equals 6. Let's collect everything on one side. X plus 2, take away 4t, take away another t equals 6. Therefore, x is equal to, bring the negative 5t to the other side, bring the 2 to the other side to get 5t minus plus 4. So my line, my line would be, okay, the point doesn't really matter since we don't need it, but let's write it down anyway. The point would be 4, 1, 0 plus t, and then I look at the numbers attached to t now. The x coordinate attached to t is 5, the y is negative 2, the z is 1, and t is in the real numbers. Therefore, the answer to the question is the same thing I just wrote, but not with 410, but with the question, the thing I was supposed to have. So 5, negative 2, 3. Okay, now let's just quickly draw a picture of this before we close off for the day. So let's just quickly change this plane. So this was x plus 2y minus z equals 6, and this one was y plus 2z equals 1. Okay. Now, I said that these things are supposed to intersect. Okay, what did I say here? So the point was 4, 1, 0. The direction vector was 5, negative 2, and 1. And if I look at that line, so let's hide this for a sec. Okay, so my line looks good. Looks like it intersects both of them, as it should. Okay. Now, of course, I don't want this line. I want a line that goes through 5, negative 2, 3. So it has to pass through that point P, but it has to be parallel to the one we just did. So we'll go line, point P with the same direction vector M1, and you get a parallel line. It's parallel to the intersection of the two planes, but it is, it passes through P instead of something else. So 5, negative 2, 3 plus 5, negative 2, 1. And that's the answer. Okay, so there's some text work to try. I think there's an assignment that goes with this. Don't quote me on that, but you can have a look. And again, please post any questions.